At 4 a.m., on March 28, 1979, 3 Mile Island Unit 2, a Babcock and Wilcox pressurized water reactor operating at 97% power near Middletown, Pennsylvania, experienced a feedwater pump failure in its secondary system. The turbine tripped automatically, the reactor scrammed as designed, primary system pressure rose to 2,255 psi, triggering the pilot-operated relief valve atop the pressurizer. Standard transient response, exactly what operators had trained for hundreds of times. The relief valve should have closed when pressure dropped to its reset point. Control room indicators suggested it had. The pressurizer level gauge read high, confirming to operators that the primary system remained properly filled with coolant. Automatic safety systems functioned correctly. Emergency core cooling pumps activated, then were manually throttled back per procedure when pressurizer level appeared adequate. Yet beneath these reassuring signals lay a fundamental design contradiction. The pressurizer level measurement was physically accurate, but diagnostically false. The instrument reported liquid inventory, while the reactor vessel itself was losing coolant mass through an undetected path. Training doctrine had conditioned operators to interpret high pressurizer level as proof of adequate core cooling. The plant's information architecture made this interpretation inevitable and wrong. The Babcock and Wilcox pressurized water reactor design represented a specific engineering philosophy that distinguished it from other reactor vendors. Unlike Westinghouse or General Electric designs, the B&W approach emphasized the pressurizer as the primary diagnostic tool for system inventory management. This design choice carried profound implications for operator training, emergency procedures, and ultimately, accident progression. The pressurizer in a B&W plant functions as both a pressure control device and, critically, as the operator's primary window into primary system inventory. This cylindrical vessel, connected to the reactor coolant system's hot leg, contains both liquid water and steam. During normal operation, electric heaters and spray systems maintain precise pressure by controlling the steam-water interface. The liquid level within this vessel was intended to reflect the overall inventory of the primary cooling system, a logical assumption under steady-state conditions. According to NRC documentation from the 3 Mile Island investigation, B&W's training philosophy taught operators that pressurizer level directly correlated with reactor vessel liquid inventory. This correlation formed the foundation of emergency procedures. When pressurizer level appeared adequate, operators could assume the reactor core remained covered with coolant. When level dropped, emergency core cooling systems would inject additional water to restore inventory. This binary logic, high level equals adequate cooling, low level requires injection, became deeply embedded in operator mental models. The physical reality underlying this design assumption was more complex than training suggested. The pressurizer connects to the primary system through a single surge line attached to the hot leg piping. Under normal conditions, this connection ensures hydraulic communication between the pressurizer and the reactor vessel. Temperature changes, pressure transients, and normal operational variations cause water to flow back and forth through this surge line, maintaining equilibrium between pressurizer level and system inventory. However, this equilibrium depends on several critical assumptions that B&W designers considered permanent. First, that the primary system boundary remains intact. Second, that fluid conditions remain single-phase throughout the system. And third, that hydraulic communication through the surge line accurately reflects reactor vessel conditions. When these assumptions fail simultaneously, pressurizer level can provide information that is instrumentally correct but physically misleading about the actual state of reactor core cooling. The control room instrumentation reflected this design philosophy through its emphasis on pressurizer parameters. Large, prominent indicators displayed pressurizer level and pressure. Reactor vessel level, a direct measurement of coolant coverage over the fuel, was not provided. This absence was not an oversight but a deliberate design choice based on the assumption that pressurizer level provided sufficient information for inventory management. Direct reactor vessel level measurement was considered unnecessary given the presumed reliability of pressurizer indication. Training procedures reinforced this instrumentation hierarchy. Simulator exercises emphasized pressurizer level as the primary parameter for emergency response decisions. Operators learned to respond to low pressurizer level by initiating emergency core cooling injection and to high pressurizer level by throttling injection flow. These responses became automatic, requiring minimal conscious decision-making under stress. The procedures assumed that pressurizer level would always provide accurate guidance for these critical actions. Emergency operating procedures reflected this same assumption structure. The immediate actions for loss of coolant accidents focused on pressurizer level restoration, rather than direct verification of core cooling adequacy. Procedure writers assumed that restoring pressurizer level would automatically ensure adequate reactor vessel inventory. This assumption eliminated the need for complex diagnostic steps that might delay critical safety actions during rapidly developing accidents. The technical basis for these assumptions rested on extensive analysis of design basis accidents, scenarios that reactor designers considered credible and analyzed thoroughly during plant licensing. These analyses demonstrated that pressurizer level would indeed reflect reactor vessel inventory during large break loss of coolant accidents, steamline breaks, and other postulated events. Computer simulations confirmed that emergency core cooling systems, guided by pressurizer level indication, could successfully mitigate these scenarios. What these analyses did not fully explore were the implications of small break loss of coolant accidents combined with two-phase flow conditions in the reactor vessel. During such events, steam formation within the reactor vessel could cause the pressurizer level to rise even as overall system inventory decreased. This counterintuitive behavior, rising pressurizer level during inventory loss, fell outside the envelope of thoroughly analyzed scenarios. The physics underlying this behavior involves the complex interaction between steam generation, pressure changes, and fluid communication through the pressurizer surge line. When steam forms in the reactor vessel due to inadequate cooling, this steam occupies volume that was previously filled with liquid water. As the steam-water mixture expands, it can push liquid water backward through the surge line into the pressurizer, causing pressurizer level to rise. Simultaneously, actual liquid inventory in the reactor vessel decreases as steam continues to form and coolant continues to escape through whatever breach initiated the transient. This physical phenomenon creates a diagnostic trap. The very indicator that operators depend on to confirm adequate cooling provides false assurance precisely when cooling is most critically threatened. The pressurizer level instrument functions correctly. It accurately measures the liquid level within the pressurizer vessel. But the information this measurement conveys about reactor vessel conditions becomes fundamentally unreliable under two-phase flow conditions. B&W's design team understood the theoretical possibility of such conditions, but considered them highly unlikely given the multiple barriers that would prevent small break accidents from developing two-phase flow in the reactor vessel. Primary among these barriers was the assumption that operators would quickly identify and isolate small breaks, preventing inventory loss from reaching levels that could cause significant steam formation. Additionally, emergency core cooling systems were sized to easily compensate for small inventory losses, making sustained two-phase conditions seem implausible. The training program for B&W operators reflected these design assumptions through its emphasis on rapid transient recognition and appropriate emergency system actuation. Operators learned to distinguish between different types of accidents based on characteristic parameter patterns. Large break accidents would show rapidly decreasing pressurizer level, requiring immediate high-rate injection. Steamline breaks would show characteristic pressure and temperature signatures. Small breaks, if they occurred, would be readily identifiable through gradual inventory loss patterns that allowed deliberate, methodical response. What operators did not train for was the possibility that their primary diagnostic tool could provide systematically misleading information during the most critical phases of an accident. Simulator training scenarios maintained the assumption that pressurizer level reliably indicated system inventory status. Operators never experienced situations where high pressurizer level coexisted with inadequate reactor vessel inventory, because such scenarios were considered beyond the realm of credible accident progression. The regulatory framework supporting B&W's design approach accepted these assumptions as technically sound. Nuclear Regulatory Commission safety analyses evaluated the adequacy of emergency procedures and control room instrumentation, based on the presumption that pressurizer level would provide reliable guidance for operator actions. Licensing reviews confirmed that B&W's approach met regulatory requirements for safe shutdown and accident mitigation given the validity of underlying design assumptions. This regulatory acceptance extended to the absence of direct reactor vessel level indication in B&W plants. While some reactor vendors provided multiple independent means of assessing core cooling adequacy, the NRC accepted B&W's position that pressurizer level provided sufficient information for safe operation. This acceptance reflected the general industry consensus that proven design approaches, supported by extensive analysis, provided adequate safety margins for postulated accident scenarios. The result of these converging design, training, and regulatory decisions was a control room environment that prioritized pressurizer indication while providing operators with limited alternative means of assessing reactor vessel conditions. When pressurizer level indicated adequate inventory, operators had strong reasons, both technical and procedural, to conclude that reactor cooling was satisfactory. The entire system of instrumentation, procedures, training, and regulation supported this conclusion. Understanding this design foundation is essential for analyzing what occurred during the early morning hours of March 28, 1979. The operators who would soon face critical decisions about emergency core cooling injection were not simply following arbitrary procedures or making intuitive judgments. They were implementing a coherent technical philosophy that had been validated through extensive analysis, accepted by regulators, and reinforced through years of training. Their actions reflected not individual failures, but the systematic application of design assumptions that would prove invalid under the specific conditions that developed that morning. The stage was thus set for a confrontation between engineering logic and physical reality, a confrontation in which technically correct instrument readings would lead to operationally incorrect conclusions, and procedural compliance would amplify rather than mitigate the developing crisis. The instrumentation philosophy that governed 3 Mile Island Unit 2's control room design created the conditions for operator confusion, but it required specific latent weaknesses to transform that confusion into irreversible consequences. These weaknesses existed not as dramatic failures, but as subtle degradations in the plant's ability to provide clear, unambiguous information during crisis conditions. The pilot-operated relief valve, the alarm system design, and the emergency procedure structure each contained vulnerabilities that would align with devastating precision on March 28, 1979. The pilot-operated relief valve atop the pressurizer had exhibited problematic behavior in previous months, establishing a pattern of unreliable operation that plant maintenance records documented, but that control room indication systems could not adequately communicate to operators. This dresser valve, designated as PORV RCR2, had a history of failing to close properly after opening during pressure transients. Maintenance work orders from late 1978 indicated multiple instances where the valve required manual closure or repair after sticking in the open position. According to NRC investigation records, the PORV had been replaced in October 1978 due to seat leakage problems. The replacement valve was of identical design but had not undergone the extensive testing that would reveal its tendency to stick open under certain pressure and temperature conditions. Plant personnel were aware of generic PORV reliability issues affecting the industry, but this awareness had not translated into enhanced monitoring capabilities or modified procedures that could quickly identify valve position discrepancies. The control room indication for PORV position represented a fundamental weakness in the plant's information architecture. Operators could observe whether the valve had received an open signal and whether it had received a closed signal, but they had no direct indication of actual valve position. The control room display showed valve demand status, what the control system was commanding the valve to do, rather than valve response status, what the valve was actually doing. This distinction, seemingly minor during normal operations, would prove critical during accident conditions. The indication system logic reflected a broader design assumption that components would respond reliably to control signals. When the pressurizer pressure decreased below the valve's reset point, the control system would send a close signal, and the control room indication would show the valve is closed. Operators had no reason to doubt this indication because it had proven reliable during previous transients and because no alternative indication was available to suggest otherwise. The absence of direct valve position feedback was not unique to TMI-2, but represented standard industry practice based on component reliability expectations. Downstream indication that could reveal continued PORV operation existed, but was not designed to provide clear diagnostic information to control room operators. Temperature measurements in the PORV discharge piping could indicate flow through the valve, but these temperatures required interpretation and comparison with normal values. During a complex transient with multiple systems responding simultaneously, operators would need to actively seek out and analyze this information, rather than having it prominently displayed or alarmed at abnormal conditions. The pressurizer relief tank, which collected discharge from the PORV, provided another potential source of information about valve position. Rising temperature or pressure in this tank could indicate continued flow from the PORV even after the valve should have closed. However, this information was not processed by the control room alarm system in a way that would clearly identify PORV malfunction. Temperature and pressure changes in the relief tank occurred during normal PORV operations, making abnormal conditions difficult to distinguish without careful analysis that emergency situations rarely permitted. Plant alarm systems compounded these indication weaknesses through their design philosophy and technical limitations. The TMI-2 control room used a conventional alarm system based on individual parameter thresholds rather than integrated system status assessment. When multiple plant parameters exceeded their alarm set points simultaneously, operators received a cascade of individual alerts without clear prioritization or systematic guidance about which alarms indicated root causes versus secondary effects. During the initial stages of the March 28 transient, the alarm system would register dozens of individual parameter deviations within the first few minutes. Pressurizer pressure alarms, level alarms, temperature alarms, pump status alarms, and emergency system actuation alarms would all activate in rapid succession. The alarm annunciator system, designed for steady-state operations where individual parameter deviations occurred infrequently, could not effectively communicate the integrated plant status that operators needed for rapid transient assessment. The alarm printer, which provided a chronological record of alarm activations, would quickly fall behind real-time events as the transient developed. This delay meant that operators could not rely on the alarm sequence to understand the progression of plant conditions. Critical alarms indicating PORV discharge line temperature increases or relief tank pressure changes would be buried among numerous other alarms, making pattern recognition extremely difficult under time pressure. Training programs for TMI-2 operators reflected these system limitations through their emphasis on individual component response rather than integrated diagnostic reasoning. Simulator scenarios typically involved single failure events that produced clear alarm patterns pointing toward specific emergency procedures. Operators learned to respond rapidly to these characteristic patterns without developing extensive experience in sorting through complex, multi-component alarm states where the root cause might not be immediately obvious. The training approach assumed that emergency procedures would provide adequate guidance once operators correctly identified the type of event occurring. Procedure writers designed emergency operating procedures as branching logic trees that guided operators through systematic diagnostic steps based on observed plant parameters. However, these procedures assumed that key plant parameters, particularly pressurizer level, would provide reliable information for decision-making. Emergency core cooling system procedures exemplified this assumption-dependent structure. The high-pressure injection system was designed to operate automatically upon receiving actuation signals from low pressurizer pressure or high containment pressure. Once actuated, the system would inject water into the primary system until operators manually controlled or terminated injection based on pressurizer level indication. The procedures explicitly directed operators to reduce injection flow when pressurizer level indicated adequate system inventory. This procedural logic created a potential trap during conditions where pressurizer level provided misleading information about actual reactor vessel inventory. If two-phase conditions in the reactor vessel caused pressurizer level to rise while core cooling deteriorated, procedures would direct operators to reduce emergency injection precisely when increased injection was most critical. The procedures contained no alternative diagnostic criteria that could override pressurizer level indication when that indication became unreliable. Operator training emphasized rapid, decisive action based on procedure compliance rather than extensive independent analysis of plant conditions. This approach reflected both the complexity of nuclear plant operations and the time constraints of emergency response. Operators could not be expected to perform detailed engineering analysis during rapidly developing transients, so procedures had to provide clear, unambiguous guidance based on readily observable parameters. The training philosophy reinforced confidence in procedure compliance as the primary means of ensuring safe plant response. Shift organization and communication practices further influenced how information flowed during emergency conditions. The TMI-2 control room operated with a typical utility structure: a shift supervisor overseeing overall operations, control room operators responsible for specific plant systems, and auxiliary operators stationed throughout the plant to operate equipment and monitor local conditions. During normal operations, this structure provided adequate coordination and information sharing, emergency procedures, specified communication protocols, and decision-making authority during upset conditions. The shift supervisor would assume overall command of emergency response, while control room operators implemented specific procedure steps. Auxiliary operators would report local equipment status and execute manual actions as directed from the control room. This organization had proven effective during previous transients and training exercises that followed predictable patterns and produced clear diagnostic information. However, the communication structure depended on reliable information flow from instrumentation systems to control room operators and from operators to supervisory personnel. When instrumentation provided ambiguous or misleading information, the communication system could amplify uncertainty rather than resolve it. Multiple operators observing the same misleading indications would tend to reinforce each other's interpretations rather than challenge fundamental assumptions about what those indications meant. Organizational factors also influenced how quickly operators would question apparently normal indications during abnormal conditions. Plant culture emphasized conservative decision-making and procedure compliance as primary safety measures. Operators were trained to trust instrumentation unless clear evidence indicated instrument malfunction. Questioning the validity of apparently normal readings required a level of diagnostic skepticism that could conflict with the rapid response mentality necessary for effective emergency response. Maintenance practices related to instrumentation calibration and testing provided another layer of confidence in instrument reliability that could inhibit diagnostic questioning during emergencies. Regular calibration programs ensured that instruments read accurately when compared to reference standards. Functional testing verified that instruments responded properly to input changes. These programs gave operators justified confidence in instrumentation accuracy under normal conditions. However, calibration and testing programs could not validate instrument performance under all possible accident conditions. Pressurizer-level instruments calibrated for single-phase liquid conditions might provide accurate readings that were diagnostically invalid during two-phase flow conditions. The instruments would pass all routine tests while retaining the potential to mislead operators during precisely the conditions when accurate information was most critical. Regulatory oversight and industry experience further reinforced confidence in existing instrumentation and procedural approaches. The Nuclear Regulatory Commission's licensing process had approved TMI-2's instrumentation design as adequate for safe operation. Industry experience with similar plants had demonstrated successful transient response using pressurizer-based emergency procedures. Operators had no regulatory or experiential basis for questioning fundamental design assumptions about pressurizer level reliability. The result of these converging factors was a control room environment where multiple information sources, instruments, procedures, training, and experience, would consistently point toward the same conclusion when that conclusion was wrong. Pressurizer level would appear adequate. Procedures would direct reduced emergency injection. Training would support confidence in this response, and experience would provide no contrary examples. The latent conditions necessary for systematic operator error were completely in place. What remained was a specific sequence of equipment malfunctions and plant conditions that would activate these latent weaknesses simultaneously. The PORV would need to stick open without clear indication of its position. Emergency systems would need to respond in ways that masked rather than revealed the developing problem. Plant parameters would need to behave in ways that fell outside operator training and experience, while remaining within the bounds of apparently normal indication ranges. All of these conditions would converge during the early morning hours of March 28, 1979, transforming latent weaknesses into active failures with consequences that no single component malfunction could have produced. The transition from routine operations to irreversible crisis began with a mechanical failure that should have been manageable within the design envelope of 3 Mile Island Unit 2's safety systems. At 4:37 a.m. on March 28, 1979, the main feedwater pumps tripped offline due to a malfunction in the condensate polisher system, interrupting the flow of cooling water to the steam generators that remove heat from the reactor's primary system. This initiating event, loss of main feedwater, represented a well-understood transient for which the plant possessed multiple engineered safeguards and for which operators had received extensive training. The automatic plant response proceeded exactly as designed. Within seconds of the feedwater pump trip, steam generator water levels began dropping as residual heat continued converting water to steam without makeup flow. The turbine protection system detected the loss of feedwater and automatically tripped the main turbine offline to prevent damage from inadequate cooling. The reactor protection system responded to the turbine trip by automatically inserting control rods and shutting down the nuclear fission process. These actions occurred without operator intervention and represented the first layer of defense in depth, protection, functioning precisely as intended. Primary system conditions immediately following the reactor trip reflected normal post-shutdown physics. Decay heat from radioactive fission products continued generating approximately 6% of full power even with the reactor shut down, requiring continued cooling through the steam generators. With main feedwater unavailable and the reactor trip reducing heat generation, primary system temperature began rising as the steam generators lost their heat removal capacity. Primary system pressure increased from its normal operating value of approximately 2,155 psi toward the pressurizer relief valve set point of 2,255 psi. The pilot-operated relief valve opened at 4:37 a.m. when primary pressure reached its set point, performing its design function of preventing excessive pressure that could challenge primary system integrity. Steam and water discharged from the pressurizer through the PORV into the pressurizer relief tank, allowing primary pressure to decrease. Under normal circumstances, the valve would close automatically when pressure dropped to approximately 2,205 psi, terminating the discharge and allowing pressure to stabilize at a safe level below the relief set point. Control room indications at this point showed what appeared to be normal post-trip plant behavior. The reactor had shut down successfully. Primary pressure had peaked and was decreasing through the relief valve. Pressurizer level initially dropped due to system shrinkage as temperature decreased following shutdown, then began recovering as the pressure reduction slowed. Emergency feedwater pumps had started automatically to restore steam generator cooling capacity. All automatic actions were proceeding according to design expectations. However, a critical divergence from normal behavior was occurring beyond the operator's direct observation. The PORV failed to close when primary pressure decreased below its reset point. The valve remained fully open, continuing to discharge primary coolant to the pressurizer relief tank, even though the pressure condition that justified its operation had passed. This mechanical failure transformed a routine transient into a small break loss of coolant accident, but the control room indication provided no clear signal of this transition. The P or V position indication in the control room showed the valve as closed once the electrical signal commanding closure had been sent. Operators observed that the open light was no longer illuminated, confirming that the valve should have closed based on pressure conditions. They had no direct indication that the valve remained physically stuck in the open position, continuing to create a breach in primary system integrity. The absence of this critical information meant that subsequent operator actions would be based on an incomplete understanding of actual plant conditions. Emergency core cooling systems activated automatically as primary pressure continued decreasing due to the unrecognized coolant loss through the stuck POR-V. The high-pressure injection pumps started when pressurizer pressure dropped below their set point, beginning to inject borated water into the primary system to compensate for inventory loss. The emergency core cooling system response was appropriate for the actual plant condition, a small break loss of coolant accident, but appeared unnecessary to operators who believed the primary system remained intact. Primary system inventory loss through the stuck POR-V proceeded at a rate of approximately 220 gallons per minute, small enough that the high-pressure injection system could initially compensate for the loss while maintaining pressurizer level. However, the continued energy removal through the break, combined with decay heat generation, began creating thermal hydraulic conditions within the reactor vessel that would invalidate the fundamental assumption underlying pressurizer level indication. The emergency feedwater system, which should have restored steam generator heat removal capacity, experienced delays due to operator oversight regarding block valve positions. Emergency feedwater pumps operated correctly, but closed block valves prevented flow from reaching the steam generators for several crucial minutes. This delay extended the period during which the steam generators provided inadequate heat removal, contributing to primary system heat-up and complicating the operator's assessment of overall plant response. During these initial minutes, operators focused on restoring feedwater flow to the steam generators while monitoring what appeared to be normal emergency system response throughout the primary system. Pressurizer level had recovered to normal range following the initial post-trip shrinkage. Emergency injection flow was maintaining primary system inventory despite what appeared to be normal system leakage. Primary pressure had stabilized below the relief valve set point. All visible indications suggested that automatic systems were successfully managing the transient. The first clear deviation from expected behavior became apparent through pressurizer level trends rather than direct indication of the POR-V malfunction. Approximately 10 minutes into the transient, pressurizer level began rising above its normal operating range, despite continued emergency injection flow. Under normal circumstances, high injection flow with low system pressure would cause pressurizer level to increase, but the rate and extent of the increase exceeded what operators expected based on injection flow rates and system conditions. This pressurizer level increase reflected the onset of conditions that would prove central to the accident progression. Steam formation within the reactor vessel due to inadequate heat removal combined with continued inventory loss through the POR-V. As decay heat continued generating steam faster than the compromised steam generators could remove it, steam voids began forming in the upper regions of the reactor vessel. These voids occupied space previously filled with liquid water, causing the liquid-steam mixture to expand and push liquid backward through the pressurizer surge line. The physics underlying this phenomenon involved complex interactions between heat addition, pressure reduction, and two-phase flow behavior that had not been thoroughly analyzed during plant design or extensively covered in operator training. Steam formation in the reactor vessel created a compressible region that responded differently to pressure changes than the solid-liquid system that design analyses assumed. As steam continued forming, the reactor vessel began transitioning from a liquid-filled condition to a two-phase condition, where steam and water coexisted in proportions that varied with elevation and local heat generation rates. Operators interpreting rising pressurizer level according to their training concluded that primary system inventory was not only adequate but potentially excessive. Emergency procedures directed them to reduce high-pressure injection flow when pressurizer level exceeded normal operating range to prevent overfilling the pressurizer and potentially lifting pressurizer safety valves. This procedural guidance reflected the assumption that pressurizer level accurately indicated total system inventory and that high level meant excess inventory that should be controlled. The decision to throttle emergency injection flow represented the first major operator action that deviated from the optimal response to actual plant conditions. While procedurally correct based on available information, this action reduced the inventory makeup rate precisely when continued inventory loss through the PORV was beginning to uncover portions of the reactor core. Operators had no indication that their action was inappropriate because all visible plant parameters supported the conclusion that injection flow reduction was necessary and appropriate. Core heat transfer conditions began deteriorating as inventory loss continued and injection flow was reduced. Water level within the reactor vessel started dropping below the top of the fuel assemblies, exposing portions of the nuclear fuel to steam rather than liquid water cooling. Steam provides significantly less heat transfer capability than liquid water, causing fuel cladding temperatures to begin rising above normal operating values. This temperature increase accelerated steam generation, creating a positive feedback loop that would prove increasingly difficult to interrupt. Reactor vessel water level, the parameter that most directly indicated core cooling adequacy, was not measured or displayed in the TMI-2 control room. Operators had no direct indication of the most critical safety parameter during a loss of coolant accident. Instead, they relied on pressurizer level as a surrogate measurement that was becoming increasingly unreliable as two-phase conditions developed throughout the primary system. This fundamental information gap meant that core uncovery could proceed without clear recognition in the control room. The thermal hydraulic conditions developing within the reactor vessel represented a transition from analyzed design basis accidents to unanalyzed territory where design assumptions no longer held. Computer codes used for safety analysis had modeled loss of coolant accidents under the assumption that emergency core cooling systems would maintain adequate injection flow throughout the transient. The codes had not extensively analyzed scenarios where operators would reduce injection flow during ongoing inventory loss based on misleading pressurizer level indication. Steam generator heat removal capacity gradually improved as emergency feedwater flow was established, but the improvement came too late to prevent the establishment of two-phase conditions within the primary system. The delayed restoration of steam generator cooling allowed primary system temperature to reach saturation conditions, where steam formation became inevitable once inventory loss reduced system pressure below the saturation pressure corresponding to core temperatures. Containment atmosphere monitoring systems began detecting small amounts of radiation as primary coolant containing fission products was released through the PORV to the pressurizer relief tank and subsequently to the containment building atmosphere. These releases remained within analyzed limits for small break accidents, but they provided the first concrete evidence that primary system integrity had been compromised. However, radiation releases during loss of coolant accidents were considered normal consequences of emergency core cooling system operation, so these indications did not immediately alert operators to the PORV malfunction. Control room conditions approximately 30 minutes into the transient reflected a complex mixture of apparently contradictory information that challenged operator understanding of plant status. Emergency systems continued operating, suggesting ongoing safety system demands. Pressurizer level remained high, suggesting adequate primary inventory. Containment radiation levels were increasing, suggesting some level of primary system leakage. Steam generator levels were recovering, suggesting restoration of normal heat removal. Each individual indication appeared reasonable, but their combination created a plant status picture that matched no training scenario or analyzed accident sequence. The path toward irreversible consequences was becoming established through this accumulation of individually reasonable but collectively misleading information. Each operator decision based on available indication was procedurally correct and technically logical, given the information provided. Yet each decision moved plant conditions further from the optimal response to actual physical conditions. The divergence between apparent plant status and actual plant status was widening in ways that would soon make recovery impossible, regardless of subsequent operator actions. What operators needed but did not possess was direct, unambiguous indication of actual reactor vessel inventory and PORV position. These two pieces of information would have immediately clarified the nature of the transient and directed appropriate response measures. Instead, they possessed surrogate indications that provided systematically misleading information precisely when accurate information was most critical for preventing irreversible core damage. The stage was set for the critical phase of the accident, where continued reliance on misleading information would drive decisions that ensured core damage became unavoidable. The plant had transitioned from a recoverable transient to an unrecognized loss of coolant accident with developing core cooling problems, but this transition remained invisible to the operators, whose actions would determine whether the situation could be stabilized or would continue deteriorating toward core melt conditions. The transition from manageable emergency to irreversible core damage occurred through a sequence of physical processes that systematically defeated both automatic safety systems and operator interventions. The fundamental mechanism driving this transition was the establishment of a positive feedback loop between steam formation, pressurizer level indication, and emergency injection throttling that would prove impossible to interrupt once initiated. Understanding this mechanism requires examining the precise thermal hydraulic conditions that developed within the reactor vessel and the mass balance relationships that governed coolant inventory behavior. By approximately 6 a.m., 2 hours after the initial feedwater pump trip, reactor vessel conditions had evolved significantly from the single-phase liquid cooling assumed by design analyses. Continued decay heat generation combined with reduced heat removal through the compromised steam generators created temperature conditions approaching saturation throughout much of the primary system. The ongoing inventory loss through the stuck PORV reduced system pressure below the saturation pressure corresponding to core temperatures, creating conditions where steam formation became thermodynamically inevitable. The critical technical artifact that would govern subsequent accident progression was the relationship between steam void formation in the reactor vessel and liquid displacement through the pressurizer surge line. As steam voids formed in the upper regions of the reactor vessel, they occupied volume previously filled with liquid coolant. This volume displacement effect, combined with the thermal expansion of the remaining liquid due to continued heating, created a net liquid displacement that pushed water backward through the hot leg piping and into the pressurizer through its surge line connection. The magnitude of this displacement was substantial enough to maintain or even increase pressurizer level despite ongoing inventory loss through the PORV. Each gallon of liquid water converted to steam at reactor operating conditions expanded to occupy approximately 1,600 times its original liquid volume. Even small amounts of steam formation could therefore displace significant quantities of liquid water from the reactor vessel into the pressurizer, creating the counterintuitive condition where pressurizer level rose while reactor vessel inventory decreased. This physical relationship created a diagnostic trap that became progressively more severe as steam formation increased. The more severely the reactor core became uncovered, the more rapidly steam formation proceeded, and the more dramatically pressurizer level would rise. Operators interpreting high pressurizer level as confirmation of adequate system inventory would be most confident in their assessment precisely when core cooling was most severely threatened. The emergency injection throttling decisions made by operators in response to rising pressurizer level directly accelerated the deterioration of core cooling conditions. High-pressure injection systems had been designed to deliver approximately 1,000 gallons per minute of borated water to the primary system during loss of coolant accidents. This injection rate was calculated to compensate for inventory loss through postulated breaks while maintaining adequate core cooling. However, when operators reduced injection flow to approximately 100 gallons per minute based on pressurizer level indication, they created a substantial imbalance between inventory loss and makeup. The mass balance governing reactor vessel inventory became increasingly unfavorable as steam formation accelerated. Inventory loss through the PORV continued at approximately 220 gallons per minute, while reduced injection flow provided only 100 gallons per minute of makeup. This net loss of 120 gallons per minute meant that reactor vessel level would continue dropping regardless of pressurizer level behavior. Additionally, each gallon of inventory lost through steam formation was effectively lost twice, once through the physical removal of liquid and again through the conversion of remaining liquid to steam that provided inferior cooling characteristics. Core heat transfer deterioration proceeded through several distinct phases as water level dropped progressively lower within the reactor vessel. Initial uncovery exposed the upper portions of fuel assemblies to steam cooling rather than liquid water cooling. Steam cooling provided approximately 1/10 the heat transfer capability of liquid water, causing fuel cladding temperatures to rise rapidly above normal operating values. This temperature increase accelerated local steam generation, creating more void space and causing water level to drop further. As more of the core became uncovered, heat transfer conditions deteriorated progressively. Fuel cladding temperatures in uncovered regions reached 1,000 degrees within the first hour of significant uncovery, well above normal operating temperatures of approximately 600 degrees Fahrenheit. These elevated temperatures initiated chemical reactions between the zirconium fuel cladding and steam that would have profound implications for both core integrity and containment atmosphere composition. The zirconium-steam reaction represented a fundamental transition from thermal stress to chemical damage within the reactor core. At temperatures above 1,200 degrees, zirconium cladding begins reacting exothermically with steam according to the reaction Zr plus 2H2O, ZrO2 plus 2H2 plus heat. This reaction both weakened the structural integrity of fuel cladding and generated additional heat that accelerated the damage process. More significantly, the reaction produced hydrogen gas that would accumulate within the primary system and eventually migrate to containment. Hydrogen production through zirconium steam reactions provided the first quantitative evidence of the extent of core damage occurring within the reactor vessel. Each pound of zirconium that reacted with steam produced approximately 0.25 pounds of hydrogen gas. Post-accident analyses would eventually conclude that approximately 1,200 pounds of hydrogen were generated during the TMI-2 accident, indicating that roughly 2,400 pounds of zirconium had been oxidized, representing oxidation of approximately half the total zirconium inventory in the reactor core. The accumulation of hydrogen within the primary system created additional complications for both heat transfer and system hydraulics. Hydrogen is essentially non-condensable under reactor operating conditions, meaning that once formed, it persists as a gas that occupies volume and impedes liquid circulation. Large quantities of hydrogen accumulating in the upper regions of the reactor vessel and steam generators created flow blockages that further reduced natural circulation cooling capability. Fuel pellet melting began as cladding temperatures exceeded 2,000 degrees in the most severely overheated regions of the core. Unlike cladding oxidation, which proceeded gradually as temperatures increased, fuel melting represented a threshold phenomenon that proceeded rapidly once initiated. Uranium dioxide fuel pellets have a melting point of approximately 2,800 degrees, but structural degradation begins at lower temperatures when cladding support is lost due to oxidation or mechanical failure. The progression of fuel damage created a positive feedback loop that accelerated core deterioration once critical thresholds were exceeded. Fuel pellet swelling due to overheating increased mechanical stress on already weakened cladding, causing additional cladding failures that exposed more fuel to steam. Molten fuel relocated to lower regions of the core where it solidified into masses with poor heat transfer characteristics, creating hot spots that drove local temperatures even higher. Core geometry changes due to fuel relocation and melting fundamentally altered heat transfer and fluid flow patterns within the reactor vessel. Molten fuel and cladding formed blockages that impeded coolant flow through fuel assemblies, creating preferential flow paths that left some regions of the core with minimal cooling while providing excessive cooling to other regions. These geometry changes made core cooling increasingly difficult even if adequate coolant inventory could be restored. The point of no return for preventing significant core damage occurred approximately 4 hours into the accident, when combination of continued inventory loss, reduced injection flow, and accelerating steam formation made core uncovery irreversible using available systems and procedures. By this time, approximately 40% of the active fuel height was uncovered, zirconium steam reactions were proceeding at substantial rates, and fuel temperatures in the most damaged regions exceeded 2,000 degrees. Recognition of the core malfunction came too late to prevent core damage but early enough to begin damage mitigation efforts. Shift supervisor William Zooey and reactor operator Craig Faust began questioning pressurizer level reliability around 6 a.m. when radiation levels in the containment building indicated substantial primary system leakage despite apparently adequate inventory indication. The discovery of high temperature in the pore of discharge line confirmed that the valve remained open despite control room indications showing it closed. Attempts to close the pore V-block valve and stop the inventory loss began around 6:18 a.m., nearly 2 hours after the valve had first stuck open. Closing the block valve successfully terminated the primary cause of coolant loss, but substantial core damage had already occurred. The restoration of emergency injection flow to design rates helped slow further damage progression, but could not reverse the core geometry changes and chemical damage that had already taken place. The thermal hydraulic conditions within the reactor vessel at this point represented a complex mixture of liquid water, steam, hydrogen, and damaged fuel debris that exhibited behavior far removed from the single-phase liquid conditions assumed by design analyses. Natural circulation patterns were severely disrupted by hydrogen accumulation and core flow blockages. Temperature distribution was highly non-uniform, with some regions approaching normal temperatures while others remained well above 1,000 degrees. Verification of core cooling restoration became extremely difficult under these conditions because normal instrumentation assumed single-phase liquid conditions and intact core geometry. Pressurizer level had lost all diagnostic value for assessing core cooling adequacy. Primary system temperatures showed wide variations that reflected localized conditions rather than overall core status. Flow measurements were unreliable due to two-phase flow and instrumentation limitations under accident conditions. The transition from inventory control to damage mitigation represented a fundamental shift in operator objectives and available tools. Standard emergency procedures focused on maintaining adequate coolant inventory and system pressure to ensure core cooling through established heat transfer mechanisms. Once significant core damage occurred, these mechanisms were no longer reliable, and operators had to develop alternative approaches based on limited information about actual core conditions. The physics governing core cooling under damaged conditions remained poorly understood in 1979 because such conditions fell outside the design basis analyzed during plant licensing. Computer models used for safety analysis assumed that emergency core cooling systems would maintain core integrity, making detailed analysis of damaged core cooling unnecessary. The TMI-2 accident represented the first test of actual reactor response under conditions that design analyses had assumed would not occur. Post-accident analysis would eventually reveal that approximately 20 tons of molten core material had relocated to the bottom of the reactor vessel, forming a debris bed with complex internal structure and heat generation patterns. This debris bed was eventually cooled by water injection, but the cooling process required months of careful monitoring and system adjustments. The successful cooling of severely damaged core materials demonstrated that core damage, while serious, did not necessarily lead to reactor vessel failure or containment breach. The mass balance relationships governing the accident progression demonstrated that instrument accuracy and diagnostic validity represented fundamentally different requirements. Pressurizer level instruments continued providing accurate measurements of liquid level within the pressurizer throughout the accident. However, the diagnostic significance of these measurements, their ability to inform operators about core cooling adequacy, was completely invalidated by the two-phase flow conditions that developed in the reactor vessel. This distinction between instrumental accuracy and diagnostic validity would become a central focus of post-accident improvements to nuclear power plant instrumentation and emergency procedures. The recognition that technically correct instrument readings could provide systematically misleading operational guidance led to fundamental changes in how plants measured and displayed critical safety parameters, particularly those related to core cooling adequacy during accident conditions. The recognition that core damage was occurring marked a fundamental transition in the accident response from routine emergency procedures to uncharted territory, where plant behavior deviated significantly from analyzed conditions. Once operators closed the PORV block valve at 6:18 a.m., stopping the primary source of coolant loss, their focus shifted from inventory control to damage assessment and mitigation. However, the thermal hydraulic conditions within the reactor vessel had evolved to a state that challenged both instrumentation capabilities and procedural guidance, creating new uncertainties that would persist for days. The immediate priority following PORV isolation was establishing reliable core cooling through emergency injection systems. Operators restored high-pressure injection flow to design rates, providing approximately 1,000 gallons per minute of borated water to the primary system. This injection rate should have been sufficient to refill the reactor vessel and re-establish normal cooling conditions, but the presence of hydrogen gas and damaged core geometry created flow patterns that differed substantially from design assumptions. The critical technical artifact governing stabilization efforts was the relationship between injection flow and actual core cooling effectiveness under two-phase hydrogen-laden conditions. Emergency core cooling system design assumed that injected water would flow directly to the reactor vessel and provide cooling through established heat transfer mechanisms. However, hydrogen accumulation in the upper regions of the primary system created flow impediments that caused injected water to follow preferential paths that might not provide optimal core cooling. Hydrogen behavior within the primary system represented a new challenge that had not been extensively analyzed during plant design. Unlike steam, which condenses readily when it contacts cooler surfaces, hydrogen remains gaseous under reactor operating conditions and tends to accumulate in high points throughout the system. Large quantities of hydrogen in the reactor vessel head and steam generator U-tubes created flow blockages that impeded natural circulation and caused injected coolant to stratify rather than mix uniformly throughout the primary system. The reactor coolant pumps, normally used to ensure adequate circulation for core cooling, presented operators with a complex decision regarding their continued operation. These large centrifugal pumps were designed to circulate single-phase liquid coolant and exhibited unstable behavior when operating with significant quantities of steam or hydrogen in the system. Pump cavitation had been observed during the early stages of the accident as two-phase conditions developed, leading to concerns about pump damage and system integrity. Pump operation decisions were complicated by competing considerations that had not been thoroughly addressed in emergency procedures. Continued pump operation could potentially improve mixing and circulation, helping to distribute injected coolant more effectively throughout the primary system. However, pump operation in two-phase flow could also cause additional system disturbances, potentially redistributing hydrogen in ways that could worsen flow blockages or create new areas of inadequate cooling. The decision to shut down reactor coolant pumps around 7:30 a.m. reflected operator concerns about pump damage and system stability, but it also eliminated the primary mechanism for ensuring uniform coolant distribution throughout the reactor vessel. With pumps secured, core cooling became dependent on natural circulation driven by density differences between hot and cold regions of the primary system. However, hydrogen accumulation and core geometry changes made natural circulation patterns highly unpredictable. Verification of adequate core cooling under these conditions required instrumentation that had not been designed for damaged core configurations. Core exit thermocouples, which measured water temperature as it left the top of fuel assemblies, provided some indication of local cooling conditions but were limited in number and geographic coverage. Many thermocouples had been damaged during the core uncovery period, leaving large regions of the core without direct temperature monitoring. The thermocouples that remained functional showed highly variable and often contradictory readings that reflected the complex temperature distribution within the damaged core. Some locations showed temperatures approaching normal values, suggesting adequate cooling, while others indicated temperatures well above saturation, suggesting continued inadequate cooling or steam formation. Interpreting these readings required understanding of local core geometry and flow patterns that operators did not possess. Primary system pressure behavior during stabilization efforts provided additional evidence of continuing thermal hydraulic instabilities. Pressure fluctuations and unexpected transients suggested ongoing steam formation and condensation cycles that indicated incomplete thermal equilibrium within the system. These pressure variations were much larger than normal and occurred without clear correlation to operator actions or system changes, suggesting complex internal processes beyond direct operator control. Containment atmosphere conditions became an increasingly important factor in stabilization efforts as hydrogen continued migrating from the primary system to containment. Hydrogen releases through the pressurizer relief tank and other leakage paths gradually increased containment hydrogen concentration toward levels that could potentially support combustion if oxygen were present. However, containment atmosphere was maintained in an inert condition through nitrogen blanketing, preventing immediate combustion hazards. Radiation levels within containment continued increasing as fission products were released from damaged fuel and transported throughout the primary system and into containment through various leakage paths. These radiation levels complicated personnel access for manual operations and equipment monitoring, requiring careful coordination of radiation protection measures with operational activities. The increasing radiation also provided continuing evidence that significant fuel damage had occurred, confirming that the accident had exceeded design basis conditions. Emergency feedwater restoration efforts proceeded in parallel with primary system stabilization, aimed at re-establishing normal heat removal through the steam generators. Emergency feedwater pumps had been operating intermittently due to operational difficulties, but sustained feedwater flow was essential for long-term core cooling through natural circulation. Steam generator heat removal provided the only reliable mechanism for removing decay heat once reactor coolant pumps were secured. The steam generator heat removal process was complicated by hydrogen accumulation in the steam generator U-tubes, which impeded natural circulation flow patterns and reduced heat transfer effectiveness. Hydrogen tends to accumulate in the highest points of the U-tubes, creating gas pockets that block liquid flow and reduce the effective heat transfer surface area. These blockages made steam generator cooling less predictable and potentially less effective than design analyses assumed. Water level control in the steam generators required careful balance between providing adequate inventory for heat removal and avoiding excessive inventory that could interfere with natural circulation patterns. Normal water level control relied on feed water flow adjustments based on steam generator level indication, but the presence of hydrogen and two-phase flow conditions in the primary system made normal level control algorithms less reliable. By mid-morning on March 28, approximately 6 hours after the initiating event, operators had achieved a tenuous stabilization of plant conditions, but faced ongoing uncertainties about the adequacy and sustainability of core cooling. Primary system pressure had stabilized at reduced levels, injection flow was maintaining apparent system inventory, and containment conditions were being controlled within acceptable limits. However, multiple indicators suggested that thermal hydraulic conditions within the reactor vessel remained far from normal. Core temperature monitoring continued showing wide variations and elevated readings in some locations, suggesting that thermal equilibrium had not been fully established throughout the core. The variability of these readings, combined with the known limitations of instrumentation under accident conditions, made definitive assessment of core cooling adequacy extremely difficult. Operators could not determine with confidence whether current cooling was sufficient to prevent further fuel damage or whether additional measures might be required. The hydrogen accumulation within the primary system presented a particular challenge for long-term stability because hydrogen behavior under reactor conditions was not well understood in 1979. Unlike other gases that might be present during accidents, hydrogen could not be easily removed from the system through normal purification processes. large quantities of hydrogen would remain within the system indefinitely unless specific measures were taken to either remove the hydrogen or accommodate its presence in operational decisions. Hydrogen removal techniques available at TMI-2 were limited and had not been extensively tested under accident conditions. The normal hydrogen recombiner systems were designed for small quantities of hydrogen produced during normal operations, not for the large quantities generated during zirconium steam reactions. Alternative hydrogen removal methods would require time to implement and carried their own risks and uncertainties. Communication with off-site emergency response organizations became increasingly important as the scope and potential consequences of the accident became clearer. The Nuclear Regulatory Commission had been notified early in the event, and NRC inspectors and technical staff were en route to the site to provide assistance and oversight. However, the technical complexity of the accident conditions meant that even experienced emergency response personnel faced unprecedented challenges in assessing plant status and recommending appropriate actions. The information available to emergency response personnel was limited by the same instrumentation and procedural inadequacies that challenged plant operators. Off-site personnel had to rely primarily on the same misleading or ambiguous indicators that had contributed to the accident progression. Additionally, communication difficulties and the rapidly evolving nature of plant conditions made it difficult to maintain accurate situational awareness among all parties involved in emergency response. Public information and media communication presented additional challenges as news of the accident spread beyond the immediate emergency response community. The technical complexity of reactor accidents and the uncertainties inherent in assessing damaged plant conditions made accurate public communication extremely difficult. Initial public statements necessarily reflected the significant uncertainties that surrounded actual plant conditions and potential consequences. The decision-making environment during stabilization efforts was characterized by time pressure, technical uncertainty, and limited precedent for the conditions that had developed. Operators and emergency response personnel had to make critical decisions about plant configuration and emergency actions based on incomplete information and without clear guidance from procedures or previous experience. This environment required careful balance between conservative decision-making and avoiding actions that might inadvertently worsen plant conditions. Plant configuration management became increasingly complex as multiple systems operated outside their normal envelopes and interactions between systems became less predictable. Standard operating practices assumed normal system performance and clear cause and effect relationships between operator actions and plant response. Under accident conditions with damaged core geometry and two-phase flow throughout the primary system, these relationships became highly uncertain. The morning of March 30th brought new challenges when a planned depressurization of the primary system to facilitate hydrogen removal resulted in an unexpected and significant release of radioactive material to the environment. This release occurred when a pressurizer relief valve was opened to reduce system pressure, causing radioactive gases dissolved in the primary coolant to be released through the auxiliary building ventilation system. The release was unplanned and created significant confusion among plant personnel and emergency response organizations. The Friday morning release demonstrated that plant conditions remained unstable and unpredictable more than 48 hours after the initiating event. The radioactive release provided dramatic evidence that normal plant control had not been fully restored and that additional unexpected events could occur without warning. This release prompted serious consideration of evacuation measures for the surrounding population and marked a new phase of the emergency response focused on protecting public health rather than solely on plant stabilization. Reactor vessel head hydrogen accumulation emerged as a particularly troubling concern during the weekend following the accident. Calculations suggested that significant quantities of hydrogen might have collected in the reactor vessel head, potentially creating conditions that could support hydrogen combustion if oxygen were introduced through air ingress or radiolytic decomposition of water. The possibility of hydrogen combustion within the reactor vessel raised concerns about reactor vessel integrity and potential containment failure. The hydrogen bubble concern dominated emergency response activities throughout the weekend of March 31st and April 1, as technical experts attempted to assess the likelihood of hydrogen combustion and develop mitigation strategies. Analysis of this issue required detailed understanding of hydrogen behavior, oxygen generation mechanisms, and combustion characteristics under reactor conditions, subjects that had received limited attention during normal reactor safety analysis. Resolution of the hydrogen bubble concern ultimately required recognition that oxygen concentrations within the reactor vessel were insufficient to support combustion due to the consumption of oxygen through metal oxidation reactions and the absence of significant oxygen generation mechanisms. However, reaching this conclusion required several days of analysis and consultation among experts from multiple organizations, during which the potential for reactor vessel failure remained a serious concern. The period from initial core damage recognition through hydrogen bubble resolution demonstrated the challenges inherent in managing reactor accidents that exceed design basis conditions. Standard emergency response procedures and analysis tools were inadequate for the conditions that developed, requiring real-time development of new approaches and analysis methods. The stabilization phase revealed that preventing further damage was only the first step in managing severe reactor accidents, and that achieving genuine stability could require weeks or months of continued effort. The definitive assessment of what actually occurred within the 3 Mile Island Unit 2 reactor vessel required years of forensic investigation, using techniques that had never before been applied to a commercial nuclear reactor accident. The scale of core damage and the technical challenges of examining highly radioactive materials in an inaccessible environment demanded innovative approaches to evidence gathering and analysis. These investigations would ultimately provide conclusive proof of the accident progression mechanism, while revealing fundamental lessons about nuclear plant design, operation, and regulation. The first direct evidence of core damage severity came from water samples taken from the primary system during the weeks following the accident. These samples contained fission products that could only have been released from damaged fuel pellets, confirming that fuel cladding integrity had been extensively compromised. Analysis of specific isotope ratios and concentrations provided quantitative estimates of the fraction of fuel that had been damaged, suggesting that approximately 50% of the reactor core had experienced some level of degradation. More detailed evidence emerged through gamma radiation mapping of the reactor vessel conducted using remote detection equipment lowered through penetrations in the reactor vessel head. These measurements revealed the spatial distribution of radioactive materials within the vessel, showing significant relocation of core materials from their original positions in the fuel assemblies. The radiation signature indicated that molten fuel had collected in the lower regions of the reactor vessel, forming debris beds with irregular geometry and variable material composition. The critical technical artifact that provided the most definitive evidence of accident progression was the reactor vessel head removal conducted in July 1984, more than 5 years after the accident. This unprecedented operation involved removing the massive steel head of the reactor pressure vessel to allow direct visual and physical examination of the damaged core. The removal required extensive radiation shielding and remote handling equipment due to the intense radioactivity of the damaged core materials. Direct visual examination of the core following head removal provided dramatic confirmation of the extent of damage that had occurred during the first few hours of the accident. The upper regions of many fuel assemblies had been completely destroyed, with fuel pellets and cladding materials having melted and relocated to form irregular masses in the lower portions of the core. Approximately 20 tons of molten material had collected in the bottom of the reactor vessel, forming a debris bed with a complex internal structure. The debris bed examination revealed the progression of core damage in unprecedented detail. The material consisted of previously molten uranium dioxide fuel, zirconium cladding, steel structural materials, and control rod materials that had melted together and subsequently solidified into masses with highly variable composition and porosity. Some regions of the debris were relatively dense, while others contained significant void spaces that had complicated cooling during the accident and aftermath. Core sample analysis provided quantitative confirmation of the chemical processes that had occurred during core overheating. Extensive oxidation of zirconium cladding was evident throughout the damaged regions, confirming that zirconium steam reactions had proceeded at the rates predicted by post-accident calculations. The hydrogen generation estimates based on core examination agreed closely with calculations based on containment hydrogen measurements, validating the understanding of this critical aspect of accident progression. The examination also revealed evidence of fuel pellet melting and relocation that demonstrated the thermal conditions that had existed within the core during the accident. Fuel pellets in the most severely damaged regions had reached temperatures sufficient to cause melting and flow, creating the debris structures observed during vessel examination. Temperature estimates based on material analysis suggested peak temperatures had exceeded 2,800 degrees in some core regions. Reactor vessel integrity assessment following core examination provided crucial evidence about the ultimate consequences of core melting. Despite the extensive core damage and the presence of 20 tons of molten material in the reactor vessel lower head, the vessel itself had maintained its structural integrity throughout the accident. The steel vessel head showed no signs of thermal damage or structural degradation that would have led to vessel failure and potential containment breach. The successful containment of severely damaged core materials within the reactor vessel demonstrated that core melting, while serious, did not necessarily lead to the most catastrophic consequences that had been postulated for severe reactor accidents. This finding had profound implications for reactor safety analysis and emergency response planning, showing that engineered safety features could function effectively even under conditions far beyond their design basis. Hydrogen behavior analysis based on post-accident evidence provided detailed confirmation of the hydrogen generation, transport, and accumulation mechanisms that had influenced accident progression and emergency response. Measurements of hydrogen distribution within the primary system and containment confirmed that hydrogen had migrated throughout the plant systems in patterns that matched theoretical predictions. The hydrogen bubble that had caused such concern during emergency response was confirmed to have existed but in quantities and configurations that posed no realistic combustion threat. The resolution of hydrogen bubble concerns through detailed technical analysis demonstrated both the challenges of real-time accident assessment and the importance of thorough technical evaluation before taking drastic emergency actions. The initial calculations that suggested hydrogen combustion risks were based on conservative assumptions and incomplete information about actual plant conditions. More detailed analysis using better information showed that combustion was not credible due to insufficient oxygen concentrations within the reactor vessel. Radiation release analysis based on environmental monitoring data and source term calculations provided comprehensive assessment of the accident's radiological consequences. Despite the extensive core damage, the total radiation release to the environment was substantially lower than had been feared during the emergency response. The containment building and other engineered barriers had functioned effectively to limit radioactive material release even under severe accident conditions. The environmental radiation measurements taken during and after the accident showed that the maximum radiation dose received by any member of the public was approximately 100 millirem, equivalent to about one-third of the annual background radiation dose in the area. These measurements confirmed that while the accident was severe from a plant safety perspective, the radiological consequences to the public were minimal due to the effectiveness of containment systems and the relatively small quantities of radioactive materials that were released. Long-term health studies conducted in the years following the accident found no detectable increase in cancer rates or other health effects in the surrounding population that could be attributed to radiation exposure from the accident. These studies, while limited by the inherently low statistical power available for detecting small increases in rare diseases, provided additional confirmation that the radiological consequences had been successfully limited by engineered safety systems. The comprehensive forensic investigation of the TMI-2 accident led to fundamental changes in nuclear power plant regulation, design, and operation that addressed the root causes identified through detailed analysis of the accident progression. The Nuclear Regulatory Commission implemented extensive new requirements for instrumentation, emergency procedures, operator training, and plant design that were specifically targeted at preventing similar accidents and improving emergency response capabilities. Direct reactor vessel level indication became a mandatory requirement for all operating nuclear plants following the TMI-2 accident. This instrumentation provided operators with direct measurement of coolant coverage over the reactor core, eliminating the reliance on surrogate measurements like pressurizer level that had proven unreliable under accident conditions. The new instrumentation used differential pressure measurements and other techniques that remained accurate even during two-phase flow conditions. Emergency operating procedures were completely rewritten based on lessons learned from the TMI-2 accident progression. The new procedures emphasized symptom-based response rather than event-based diagnosis, recognizing that operators might not be able to correctly identify the specific type of accident occurring, but could respond appropriately to observed plant symptoms. The procedures also incorporated multiple independent means of assessing core cooling adequacy, reducing reliance on any single instrument or measurement. Operator training requirements were substantially expanded to include extensive simulator exercises under accident conditions that had not been previously emphasized. Operators received training in recognizing and responding to small break loss of coolant accidents, degraded core cooling conditions, and severe accident management. The training emphasized understanding of underlying physical phenomena rather than rote procedure following, better preparing operators to respond effectively when plant conditions deviated from analyzed scenarios. Control room design improvements were implemented to address human factors deficiencies identified during the accident analysis. These improvements included better organization of instrumentation displays, improved alarm systems that provided prioritized information rather than overwhelming operators with multiple simultaneous alarms, and enhanced communication systems that facilitated coordination among emergency response personnel. The establishment of the Institute of Nuclear Power Operations represented a fundamental change in industry self-regulation that grew directly from lessons learned at TMI-2. INPO provided industry-wide standards for training, operations, and maintenance that went beyond regulatory minimums and emphasized continuous improvement in nuclear safety performance. The Institute facilitated sharing of operating experience and lessons learned among all nuclear utilities, helping prevent similar problems from occurring at other plants. Nuclear regulatory oversight was substantially strengthened through increased resident inspector programs that provided continuous NRC presence at each nuclear plant site. These resident inspectors conducted daily observations of plant operations and maintenance activities, providing early identification of problems that might otherwise escape detection until they contributed to more serious safety concerns. The resident inspector program represented a fundamental shift from periodic inspection to continuous oversight. Risk assessment and probabilistic safety analysis became integral parts of nuclear plant regulation and decision-making following TMI-2. These analytical techniques, which had been used primarily for research purposes prior to the accident, were applied to systematically evaluate plant vulnerabilities and prioritize safety improvements based on their potential for reducing accident risk. This risk-informed approach allowed more effective allocation of safety resources and better understanding of accident prevention strategies. The international nuclear community implemented similar improvements based on TMI-2 lessons learned, recognizing that the fundamental design and operational issues identified in the accident analysis were relevant to nuclear plants worldwide. International cooperation in nuclear safety research and information sharing was substantially enhanced, creating mechanisms for rapid dissemination of safety-significant operating experience and technical developments. The systematic investigation of the TMI-2 accident demonstrated that severe accidents could be understood through careful application of scientific and engineering principles, even when they involved complex phenomena that had not been previously experienced in commercial nuclear plants. The forensic approach used in analyzing the accident became a model for investigating subsequent nuclear events and for proactively identifying and addressing potential safety vulnerabilities before they could contribute to actual accidents. The long-term implications of the TMI-2 accident extended beyond immediate technical and regulatory changes to influence fundamental approaches to complex technological systems. The accident demonstrated that system failures could result from interactions between technically correct components when those components were operated under conditions that violated underlying design assumptions. This insight influenced safety analysis approaches in many industries beyond nuclear power. The recognition that human performance was critically dependent on the quality of information provided by instrumentation systems led to broader application of human factors engineering principles in complex system design. The TMI-2 experience showed that even highly trained operators could make systematic errors when provided with misleading information, emphasizing the importance of designing information systems that supported rather than hindered human decision-making under stress. The accident also demonstrated the importance of maintaining engineering capabilities for analyzing conditions outside the original design envelope. The most valuable technical contributions to accident management came from engineers who could apply fundamental physical principles to understand phenomena that had not been explicitly analyzed during plant design. This experience influenced educational and training approaches for engineers working with complex technological systems. Perhaps most importantly, the TMI-2 accident showed that learning from failures was possible even when those failures involved highly complex, unprecedented events. The systematic approach used to investigate the accident and implement improvements based on lessons learned became a model for continuous improvement in nuclear safety and in other high-risk industries. The accident demonstrated that technological failures, while serious, could be transformed into opportunities for fundamental safety improvements when approached with appropriate analytical rigor and commitment to learning. The legacy of 3 Mile Island Unit 2 ultimately rested not on the fact that an accident occurred, but on the systematic response to understanding why it occurred and preventing similar events in the future. The forensic investigation revealed that the accident resulted from a predictable interaction between design assumptions, instrumentation limitations, and human decision-making under uncertain conditions. More importantly, it demonstrated that these interactions could be understood, addressed, and prevented through appropriate changes to technology, procedures, training, and regulation. The plant that provided such a dramatic demonstration of the consequences of design assumption failures became an equally powerful demonstration of the possibility of learning from those failures and implementing effective corrective measures. The improvements implemented throughout the nuclear industry following TMI-2 created defense in-depth protection against similar accidents while establishing analytical and operational foundations for managing severe accidents should they occur despite preventive measures.